we'll start our course on wireless communications. My name is Ranjan Bose, Department of Electrical Engineering. Here is a breakup of the lectures. We'll start with the motivation and introduction. We'll then follow with the cellular concept and the frequency planning, which is a part of most wireless communication systems. Then we will go on and study mobile radio propagations. Fading, which is an integral impediment in most wireless communication systems, will be tackled. We'll look at the large scale path loss and then the multipath small scale fading. Then we'll look at the modulation techniques for mobile communications, followed by certain channel coding for wireless communications. Then we will look at multiple access, finally introduction to wireless networking, and if time permits, we'll look at certain wireless communication standards. So the whole series of lecture is for 42 lectures. These are the 3 suggested readings. One is a book by Professor Rappaport, Wireless Communications. We'll also take certain material from Lee, Mobile Cellular Telecommunications, and Wireless Digital Communications by Camilo Fair. Of course, a lot of material will also be taken from the various standards, and hopefully we'll have one running example, maybe the GSM phones or the CDMA 2000 1X phones as the running example for various aspects of wireless communications. Here is my contact number in case you have to get in touch with me after the classes. Alright, we start with the most fundamental question: what is wireless communications? So as we all know, wireless communication is basically transmitting and receiving voice and data using electromagnetic waves in open space, basically free from wires. Please note, the emphasis is not only on voice but also on data. So today we see people talking on the cell phones, but at the same time the mobile phones are also used to check their emails, get the stock codes, find the cricket updates, and many other things. We will soon see that the data traffic is not only giving tough competition to voice traffic, but also exceeding the voice traffic. The information from the sender to the receiver is usually carried down over a well-defined frequency band. We will soon see this frequency band, also known as the bandwidth allocated for wireless communication, is one of the most prized commodity and is usually auctioned. Then different channels can be formed, because today wireless communication is not between one person and the base station, but it is a multiple access scenario. It's a multi-user system. So we need to somehow wisely allocate the frequency channel so that we can accommodate more than one users. In fact, most of the mobile phone companies are making money because they have a very big customer base. We will look at various multiple access methods as we go along the course. Let's look at a simple example. Suppose we have an allocation of about 120 kilohertz of bandwidth, and we require to communicate from station A to station B. A very simple way is to divide the entire bandwidth into 3 sub-bands, and each one here is known as a channel, channel 1, channel 2, and channel 3, share about 40 kilohertz of bandwidth. Clearly this is idealized because we do not have the luxury to so neatly partition the bandwidth. What determines that we can have sharp cutoffs? Well, there will be a receiver with a filter, and the filter characteristics will be in part determining what kind of channel bandwidths are being actually used. So there is a difference between what you allocate and what you end up being using. So what will happen in a real life scenario is a lot of frequency overlap might take place because one of the bands trespasses on the other band. So you can have an interference. We'll look at these interference issues as we go along the course. In this idealized situation, station A can communicate through these 3 channels without the fear of interference. You have a question? Yes.
Yeah. Shouldn't we allocate a guard band?
Yes.
In an ideal situation as well.
That's right. So a good way to overcome this simple problem is to allocate some space between the frequency allocations, which are known as the guard bands. For example, channel 1 and channel 2 are not just adjacent to each other, but they have a small guard band, suppose 200 hertz of guard band in a 40 kilohertz band. We will come across the term guard bands not only for frequencies but also time guard bands when we use another technique called TDMA, time division multiple access. Here we are actually looking at an example of FDMA, the frequency division multiple access, provided 3 users are using the 3 channels. Yes.
So how do we determine the width of guard band?
How do you determine the width of the guard band? One of the ways to do it is to figure out how sharp are the roll-off factors of your filters. So if you have very sharp filters, right, you are actually throwing out all the unwanted frequencies which are not in your domain. However, if your filters are not so sharp, that is, you have put in less money to design the filters, then you need bigger, broader guard bands. Right? So it's a trade-off between the money you want to spend designing your hardware and making your hardware versus the cost of the bandwidth, because the guard band is actually not being used to send any data or voice. Yes.
Can I have more than one type of guard bands within one?
Yes. One clear example is a frequency guard band, as mentioned here. The other one could be the time guard band. Suppose different users are using different time slots for communicating. What we can do is make one user stop transmitting and start the next user begin its transmission, but we can have a short time gap between the 2 time slots. That is the time guard band. So frequency and time are the 2 most frequently used methodologies of communication. Okay. Now let's look at the basic broad level classification of wireless communications. Today, the ubiquitous wireless communication is the mobile phones. You have the mobile, but that is not the only way we communicate using wireless. The other way is to have a portability. There's a difference between mobile and portable. Mobile is complete freedom to move around, talk or communicate data on the run. However, portability is slightly different. For example, a laptop connected to a wireless local area network is said to be a portable wireless device. You can pick it up, don't worry about the wires, take it to the other part of the room and set up. So it's portable. However, that's different from being completely mobile. The third and not so popularly discussed is the fixed wireless communications. There's always an ongoing debate between fixed wireless and wireline. The major objection is, if you have fixed wireless communications, why not just put a wire and make it much more robust? What is the need for having a fixed wireless? We thought wireless is supposed to be mobile, right? However, there are clear-cut advantages that fixed wireless systems have. These advantages are the basic advantages that any wireless systems have. The first is freedom from wires, less installation time and cost. If you have wires, you have to install the wires. You have to either dig up the road or put up towers, or you have to carry them on poles. Right? But wireless means you do not have any of these problems. In fact, one of the evolving standards is the IEEE 802.16, the Wireless Metropolitan Area Network Standard, the wireless MAN standard. It is being ratified, and this is important because this is one of the first IEEE standards which will be first tested in a Southeast Asian country. Most of the IEEE standards which have been launched so far are either first tested in the US or in the Europe. The first time an 802.16 prototype will be tested in South Korea early this year, 2005. So we will also have a little bit of focus on fixed wireless access. The next thing we have to look at is the typical frequencies and how the frequency domain acquisitions work. For example, FM radio, which we all listen to these days, work around 80 megahertz. The TV broadcast is at 200 megahertz. The GSM phones work at 900 and 1800 megahertz. So the dual band phones work at two frequencies. So we are touching the gigahertz range. The GPS, global positioning systems, work at 1.2 gigahertz. PCS phones 1.8 gigahertz. The Bluetooth, the poor cousin of the ultra wideband technology, which we will also discuss in this course, works at also 2.4 gigahertz. Wi-Fi, the 802.11b, works at 2.4. 2.4 gigahertz has been a favorite band recently because it is a free band. It is also known as the ISM band, right? And it is used, it's given to the medical industry, to the institutions, to the scientific establishments to experiment with. And a lot of useful appliances have come out on this frequency band. Okay? We have a wireless lab here where most of the experiments have also been designed around the 2.4 gigahertz simply because we did not have to take any license. So it is a license-free band. Please note, I have put in numbers here, 2.4. It doesn't mean that is the only frequency that it works at. It's a frequency band all the time. However, let's not be limited by this 2.4 gigahertz. We have frequencies working at 28 gigahertz. We have frequencies working at 42 gigahertz, 60 gigahertz, and trial runs are being made at 100 gigahertz. All right. So a lot of frequencies are being experimented with. This is our favorite electromagnetic spectrum, and this tells us where we are and how much more we can exploit. This yellow strip translates to a lot of rupees for the government because it gets a lot of money by licensing the spectrum. There is a Telecom Regulatory Authority of India, TRAI, which works on this area. Here, if you see, I've started off from 1 kilohertz up to gamma rays. Of course, we cannot use all of them because there are frequency related issues. The most important thing that we need to know is that different frequencies get attenuated differently by air. Okay? So air is a frequency selective channel in the sense of attenuation. Later on, we'll also see other frequency selective properties of the channel. So for the wireless communication, air is the channel. However, if we pump in, say, 1 milliwatt of power at 20 kilohertz, it might go to a certain distance before getting attenuated beyond the receiver sensitivity. So wireless communication has to work between stations A and B, which are not co-located. They are separated by a distance. Otherwise, there's no need for a communication. However, we need to communicate over large distances. So one way is to increase the power. But any increase in the power comes at two specific costs. One is clearly the money. If you're radiating more power, your equipment is more power hungry and costs more money to operate. The other more important thing today is the radiation hazard. For example, the mobile phone that I'm using today must comply to a certain maximum radiated power constraint. There's a peak power and there's an average power. Excuse me. So we cannot just keep on increasing the power of radiation to cover more distances, because the friends and people nearby will get affected. Certain frequencies, for example the 900 megahertz, travels to quite a distance. Lower frequencies also travel large distances. Therefore, a TV tower and a radio tower can cover areas up to 5 or 10 kilometers, if not more. A typical 900 megahertz base station, which communicates with our mobile phones, can work easily up to 5 kilometer radius for the given power. But for the same power, if we increase the frequency, see we go to 2.4 gigahertz, the rays, the electromagnetic radiations will get attenuated much, much more. That is, our coverage area will get reduced. Let's go to still higher frequencies, for example 28 gigahertz. Right? There also our range comes to about 2 kilometers. Then there is another factor, which is rain, dust, fog. The higher the frequency, smaller the wavelength. In fact, at 30 gigahertz, we touch the millimeter wave. There is a whole range of communication products today which work in the millimeter range. Now, the millimeter long wavelengths, the size of the wavelengths is of the size of a raindrop. Fine? They start interacting. There is a fog or rain or big dust particles. These rays would get greatly attenuated and hence result in smaller coverage areas. Right? So on this yellow strip, it is important to know where we operate. Also from the point of view is how far can you send the rays. Microwave links have been traditionally used to communicate data over tens of kilometers. But those are point-to-point wireless links. Those are again examples of fixed wireless communications. Since we are looking at the electromagnetic spectrum, another way to do wireless communication is light. We can use simple visible light, or in fact infrared, to do communications. We will also see how these things come into picture. All of this is indeed wireless communications. We do not need wires for any of them. Fine? So as a part of this course, we will look at parts of infrared, not so much optics, but primarily radio waves. Question?
So why we go such a high frequency for wireless communication when it is having such a large extent of attenuation? Why don't we go for lower frequencies?
Okay, the question being asked is, what is the need to go to such high frequencies? Clearly, high frequencies not only get attenuated, but the other thing that I didn't mention is designing high frequency circuits itself is a challenge and it's more expensive. So why do we at all need to go to high frequencies? So the answer is that today we are getting into more bandwidth hungry applications. Multimedia is a part of any application today. We not only want an SMS, we want an MMS today. We want to send video clips. All this require a larger bandwidth. To go to a larger bandwidth, to support a larger bandwidth, we have to translate ourselves upwards to higher frequencies. So there's a center frequency and then there's a frequency band associated with it. That frequency band is your bandwidth, which will allow you high data rates. A higher bandwidth will give you a larger data rate. Okay? It's directly proportional. Of course, it depends on the modulation scheme that you use, and we'll talk about the modulation schemes later. So, until the time that we were using electromagnetic spectrum only for voice communications, lower frequencies were okay. They would travel long distances, and the bandwidth requirement was not much. Right? 4 kilohertz voice, analog, no problems. The moment I need to check my email or try to do some data download on my mobile phone or my PDA, I would like to have a little bit more bandwidth. If I'm going to have a wireless in the local loop and support digital video on demand, then I definitely need to have a much higher spectrum. Okay? Therefore, for example, the wireless MAN, the metropolitan area network, it's going to solve the last mile problem. What is the last mile problem? The last mile problem is you can take the fiber to the curb, but still taking the fiber to every home is not the reality. It's still expensive. More than being expensive, it's too much effort to take a fiber optic cable to every home. But if we need broadband, truly broadband, we need to have something like a fiber optic connectivity to the home. What people do is take the fiber to the curb and put up a tower and solve the last mile wiring problem using a wireless. So this concept has been used in the wireless in the local loop scenario, where over short distances we can have large bandwidths for transmission. So here, if you see, I have highlighted propagation characteristics are very different in different frequency bands. Okay? Not to mention the hardware design issues. A brief history. This is the guy who started it all, James Maxwell, and these are the 4 fundamental equations, the well-known Maxwell's equations, which proved that yes, magic can happen. So when he proposed this, it was a theoretical result, and it would take several decades for experimental physicists to prove the existence of electromagnetic waves and what you can do with it. So if you look at the timeline, after Maxwell proposed his theory, Hertz was the first guy who validated the theory. Okay? And then Marconi developed the first telegraphic instrument. However, this is slightly different than has been found out today. Before Marconi, J.C. Bose actually did the experiments in Calcutta and published the results. However, the credit goes to Marconi as being the discoverer of the wireless communication equipment, but J.C. Bose was the first guy who actually demonstrated it. What he did was he could remotely turn off a light or fire a gunpowder using electromagnetic radiations to demonstrate the proof of concept. And it was magic, because you sit at one corner of the room and you press a button and an explosive will go off at the other part of the room. This was the experiment he did. Right? Unfortunately, we were not good at marketing. Then, of course, initial radios were established in the 1920s. The first TV broadcast took place in 1928. This is wireless. Then in 1973, the first handheld cellular phone was unveiled. Mobile phones came into the picture in the early 80s. It started with the first generation mobile phones, which were analog, then the second generation mobile phones, which were still analog, and then the 3G phones, which get into the digital domain. The 1983 cellular AMPS service was unveiled. It was a purely analog system. In 2003, last year, the cellular subscribers in the US exceeded 150 million. In November 2004, in India, the cellular subscribers exceeded 45 million. This 45 million has another very interesting connotation, which is we exceeded the number of fixed lines phones. So for the first time in India, the number of fixed lines phones were outnumbered by the number of mobile phones. It gives us a perspective as to how important this technology, the wireless technology, is. So let's look at the reasons. These are very fundamental reasons. They may be obvious, but that makes the cash registers ring today. First of all, freedom from wires. Freedom from wires translates to less installation fee, no rewiring, no stolen wires, right? No bunch of wires running here and there. In fact, this basic reason is driving the next communication standards, the 802.15.3, the ultra-wideband communications, which will also promise a wireless desktop. Today, why should my PC be linked to my printer through a wire? Okay. Sometime back, people used infrared connectivity for printers, but you had to have a line of sight. Today, what we are working at is complete freedom without the constraint of line of sight. Global coverage. Rural areas, old buildings, buildings which are not wired, battlefields. Again, this second point is very important in driving the communications industry, the wireless communications industry. Rural areas is particularly significant for India. Today, our tele-density is way, way low, right? Close to 4 per 100 on an average. So, I'm talking about the rural tele-density. What is happening is the way to leapfrog, to take advantage of this technology, is to have a wireless coverage. Later part of this lecture, I will give you a brief perspective how wireless communication is going to affect the Indian scenario. More importantly, the battlefield scenario. We are talking about today wireless ad hoc networks. It is the buzzword because these are these reconfigurable and self-configurable wireless networks which can be quickly set up for sending data or communicating between the nodes. Vehicular communication. For example, each time I go to a toll road, I have to stop, take out cash, pay, and go. And the car behind me also has to do the same thing. Wouldn't it be great? I just go across the toll gate and a wireless reader will just read up and deduct from my account the electronic cash and pay the toll for me. I'll avoid so many traffic jams near the toll road. That will be great. RFIDs, the radio frequency IDs, it's the next big thing in the markets today. They're going to replace the barcodes. Today, everything or most of the equipment which have a barcode has to be read out. But they are passive devices. RFIDs are also passive devices, but they can be read from a distance, and they can have a little bit more smartness built into them. For example, if all my medicines on the shelf are equipped with an RFID, then automatically if they're nearing expiration, I will have an update on my PC that, okay, look, that bunch of medicines have to be replaced soon. Or some medicines are selling faster than others. I can generate more revenue by ordering them on time. And a host of other applications. So these are some of the applications which are revolutionizing the wireless communication industry. So the point that I'm trying to make is wireless communications is not just talking on your mobile phone. It's way more than that. Stay connected, basically roaming. Today I switch on my phone in Mumbai and I'm ready to talk. Absolutely no problem. Flexibility to connect several devices at the same time, right? Bluetooth protocol. Today, for example, I reach out for my wallet and give you my business card. The next best thing would be I take my mobile phone and take it close within a handshaking distance to my customer, and the phones communicate and send my business card electronically. There's no need for them to retain my card because he'll lose it anyway, right? But it's much more simpler to give your information. These are the businesses which are driving the force. Okay? Flexibility. So basic mantra is stay connected anywhere, anytime. Of course, to make this mantra realizable, a lot of other things must work. And the next big thing which has come into the picture is broadband connectivity. Okay? So all these businesses are interlinked. Of course, most of these good advantages are coming from solving certain kinds of challenges. So in the next couple of slides, let's look at what are the important challenges to be sorted out. The first and the most important thing is low power design. As I mentioned before, low power is important for two things. The first thing is it should consume less power to make your battery last longer. When you sell a mobile phone today, you say talk time so many hours, standby time so many hours. If my competitor wants to sell more, he will increase the talk time. But the standard battery remains the same. The only way the person can do it is to make the hardware less power hungry. But there is a conflicting requirement. Today, when we are sending an MMS or trying to download the stock codes or doing some kind of other multimedia application, automatically I consume more power. So a lot of research is being done to figure out ways and means to reduce power consumption. Right? The second important way to reduce power consumption is to have certain signal processing tools to ensure that I only expend power when required. I do not waste power. I can have a sleep mode. My phone should radiate only when I'm talking. Okay? Part of the circuit should be shut down. And there are several other techniques to go around it. The other challenge is to squeeze out maximum from the spectrum. Right. So if we have the finite bandwidth requirement, right, there is pre-decided capacity relations which tells us how much we can go. If you have so much spectrum, you can only send so many bits per second, provided the signal to noise ratio is so much. So the question is, how can we better use it? So people thought, and they came up with a very simple solution. Why have only one transmitter antenna and one receiver antenna? Why don't you have multiple input, multiple output systems? The MIMO. So recently the MIMO systems have come in the vogue, and we are using the same bandwidth and squeezing much more out of it by using the multiple input, multiple output systems. The other challenge is coming from the consumers. We have voice, data, multimedia. All have to be packed in. The circuits must perform. Please remember, low power requirements, low bandwidth requirements. The more number of users are there, the smaller share of the pie they get. If we cut up the bandwidth, as we looked at in the first example, the more number of users, the smaller is their share. So given a limited frequency band per user, we have to extract the maximum. Again, we'll look at the techniques to do so. Then of course, we have to obey certain human requirements. For example, if we are talking on the phone, the delay should not be greater than a certain amount. Take for example the voice over IP. So it's not clearly wireless, but today a part of the voice traffic that we send also goes over IP networks. So today IP networks, the internet protocol networks, they also are a part of the large wireless networks. Most of the voice over IP applications make sure that the overall delay do not exceed a certain value. Packet loss, it will directly translate to the quality of sound that you hear. Or if you are doing a stock code update on your mobile phone, then again the bit error rate and the packet loss rate will play a significant role. Okay? I do not want to sell a stock because I got a wrong date. Data rates, very important. If I'm streaming video, okay, I would like to have a certain kind of data rate requirements. And then traffic can be classified as continuous or bursty. And these are the different problems that have to be tackled. A bursty traffic has to be tackled in a different manner than the continuous traffic. So these challenges can also be used to our advantage. For example, if you have a bursty traffic, so I type in hello, how are you in my internet email, and then I think for a while, and then I type in my next set of the sentences. So the traffic is not continuous. It goes as bursts. Even if I'm speaking on the mobile phone, I say hello and I pause and I think, and I then say my second word or sequence of sentences. In the silence period, maybe somebody else can fit in their data traffic. Today, voice, data, multimedia, everything is going as bits. It's digital communications today. All right. So the challenge of continuous versus bursty can also be used to your advantage. So the conclusion from this slide is one size fits all protocol does not work. You have to work for different protocols differently. Wired networks use this approach because they had only one kind of instrument and they didn't succeed very much. Let's look at the other set of challenges. Network support. For user mobility, we have to give them enough mobility. So if a person is traveling in a car at 50 kilometers an hour and it moves from one cell to another cell, then the handover must take place. That is, one base station must hand over the call to the next base station. We'll talk about these issues in greater details when we look at the cellular concept and handover issues. But these are challenges, because if I'm going not at 50 kilometers an hour, but at 100 kilometers an hour, I might just drop the call. Okay. Quality of service. this is again a big buzzword. Quality of service means different things to different users. The quality of service for a rich customer is different from a poor customer. Okay? Quality of service is different for different applications. But in general, we have to maintain a set of parameters. It could be the number of packet loss, the delay, the bit error rate, the noise, the background noise, and so many other things which will constitute the quality of service. Connectivity and coverage. Today, if a new internet service provider comes in or a new mobile phone service provider comes in and says, I can give only coverage to 80% of the city, he cannot sell, however good the service is. He has to give 99% coverage. Even if he has to give a coverage over the hilly regions of Uttaranchal, he has to set up wireless communication systems and then give the coverage. Coverage is a big issue. Cost efficiency. So today a handset costs 2500 rupees, it should go down to 1500 rupees tomorrow, and only then you can make money out of the business. The third set of challenges are non-business issues. They are more technical challenges, and those are the issues which will be looked at as a part of this course. The first and the foremost is fading. What is fading? Fading comes usually from multipath, because when you have a transmitter and a receiver, the rays travel not directly but comes through several reflections. So the rays have the luxury to travel from the transmitter to the receiver through multiple paths, and hence multipaths. But when they reach at the receiver, they superimpose. The simple superposition theorem must work, because how do I pick up signals at my receiver? There's an antenna, and any radiation that strikes the antenna generates an electric current. But if more than one radiations come at the same time, delayed but at the same time from different transmissions, then they superimpose. If they constructively add up, you get something different. If they destructively add up, you get something different. In essence, what you receive is very different from what you send. This would not have been the case if it was a clear line of sight communication without multiple rays. So the multipath is the culprit. This effect is called fading, because sometimes if you look at the signal or if you hear the voice goes up and down, just like when you look at or hear the shortwave radio, you would hear the voice waxing and waning. The intensity goes up and goes down, it drones. Just like fading. So this is one of the most difficult challenges to take care of. In a room environment, suppose I am going to have a wireless local area network setup, I will have a much severe path, because there are so many wall reflections through various walls, different room scenarios, to the tables, chairs and other equipment, that the multipath effect is even worse. So when we look at, for example, A22.11b, we will definitely consider the fading scenarios. Multipath I've already mentioned. Then probability of data corruption, because wireless communication by definition are not so robust unless you add in error correcting techniques. We'll look at these error correcting techniques also in this course. Security, that's the biggest problem. Anybody can put up an antenna and listen to what you're saying. So today most of the mobile phones have built security system. Okay. But for every lock that is made, some hacker will make a key. So this is an ever evolving research area for privacy, for authentication. So wireless versus mobile, just to emphasize the point, wireless doesn't necessarily mean it's mobile. Wireless systems can be fixed or ported to mobile, so we should make a difference and treat the problems differently. So fading, for example, will not be so severe for the case of fixed broadband wireless access as opposed to mobile, because as we move along, we have different paths of reflections. The reflection scenario changes and the fading also changes. Right? But somebody observed the following: the way things are progressing. When initially TV was invented, most of the transmission was through air. You had a TV tower and you had an antenna on your TV and you got TV reception by air. And when telephone was invented, you had a telephone wire coming to your home and the wired phone. Today, the TV is through cables. All the TV channels are coming through wires, and the phone is through air. So today the phone is wireless, the TV is wired. When it was invented, the TV was wireless, the phones. See how the technological innovation. So at this time we'll conclude the first session, and the types of wireless communications will be started off as the first slide of this series of lectures. Thank you.